All right. So, any questions from like last year that has been rolling around in anybody's mind that you were going, boy, when we get back in 2019, I'm going to ask John that one thing that's burning. No? Okay. So we've gone from the backyard, what you see looking up at night a couple of years ago, all the way up to the large scale structure of the universe itself. And now we're going to kind of clean up in the corners that we want to unify everything. We want to make the big and the small all make sense together, and they don't. And that's a problem that keeps astronomers up at night. So, and physicists and mathematicians, and if my information approach to this stuff is correct, then it's keeping computer scientists up at night as well. I'm getting a laser here. So we have all of these great unifications that have occurred with electricity and magnetism and light, electromagnetism, the weak interaction, explaining beta decay and neutrinos, and bringing them into electroweak interactions. All of that got put together in a very nice standard model of quantum mechanics that helped launch the modern information age. We've got Earth's gravity and celestial mechanics, and gravity and space-time geometry, very, very successful as well. As far as we hammer at these two major pillars of physics, they withstand all the tests. They're doing great. We look for holes, we look for new physics, we look for superparticles, we look for all sorts of dangling things that would give us more PhD opportunities out there. And so far, they're just not there. I mean, people are coming up with modified Newtonian dynamics to try to replace general relativity, and general relativity does the best job. And what we want in science, going the biggest picture, is to take observations, explain the past, and how we got to where we are now, and predict the future. So once you get yourself in this functional mode with physics, people are pretty happy. But there are weird things in both, and the fact that they don't work together is a problem.
Which does string theory go?
String theory is attempting to put the two together, but it's basically working here in the quantum mechanical world. And we're going to go right into that, so thank you for the segue. All right. So we have force carriers. Those are the particles. In the previous slide, it was gluons, bosons, photons, gravitons. You got strong, weak electromagnetism and gravity. And we don't have a theory of quantum gravity that would put these things together. We don't have grand unified theory. We don't have the theory of everything. So we don't have any observation of gravitons either. We have theorized properties of these things, but they are very, 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 very low energy, or low mass.
So what is dark energy and dark?
They don't fit in here. That's a problem.
Would that be an alternative to gravity?
Well, that's what modified Newtonian dynamics is trying to say, is that, all right, we don't need a new mystery particle that already doesn't have a place. We would just change how gravity operates on the larger and larger scales. But it doesn't fit observations as good as general relativity plus a particle that doesn't interact with electromagnetism. So what is this theory of everything that we're shooting for? Will it unify forces? We hope so. We'll explain the origin and the end of the universe. It'll certainly contribute to that. We'll explain life on Earth, not directly. We'll explain why we are here. That's pretty philosophical, and it won't explain why you had eggs and toast in the morning. But now, a book that I am reading right now, this is the Once and Future Turing, has an article by Scott Aronson, who's a quantum physicist, complexity specialist, and quantum computational expert. He's given a bunch of TED Talks. Wrote a textbook in oh, come on, quantum mechanics, and his book, Quantum Computing Since Democritus. So I don't know, I haven't started that one yet. Actually says you can make that jump. There is a way to bring in a type of randomness needed that gives mammals, at least, mammal brains as far as we know, the ability to have free will. Now, we're not going to get into that here, but because I'm still trying to figure out if he's a crackpot. But apparently the quantum physics world doesn't think he is. But the basic idea there is that if we don't have any randomness in our brains, then we're just analytical machines running through algorithms. And so we have this illusion of free will, but we're just computationally popping out decisions as we go. What people have brought in is the quantum strangeness. Like, all right, so if you have particles that are in superpositional states and then they into a decision, and this somehow affects how the neurons work or communication in the brain happens, then that would be an avenue for introducing randomness that you could pop into one decision or another in a way that isn't deterministic. He doesn't think so. He thinks, well, it's still on a large scale probabilistic. You have 30% chance to 70% chance of this happening, or 50-50 of the reaction happening. So you still aren't in randomness. So he proposes something called a free bit and actually links it with the Big Bang. So it's really out there. I do not know. So that's what I'll be laying on the couch over this long weekend and enjoying this. So let's get back to what we do know. Is that gravity is fantastically weak compared to all the other forces, and quantum mechanics and Einstein's general relativity do not get along. So on the largest scales, we have general relativity helping us figure out how the physics of the large universe working with the curvature of space-time. We think we're pretty darn flat from observations of the of supernova and the cosmic microwave background radiation. All this is all stuff we've covered over this last year. And we know that the baby picture of the universe painted in the cosmic microwave background radiation here has slightly warmer and slightly cooler spots that are an imprint of the early quantum fluctuations in the very tiny hot universe. So this is like frozen out snapshot of some random earlier phase. So
John, how do you define random?
okay, that's really hard. Oh my goodness. All right.
It's a human construct that, it doesn't actually exist, or...
Yeah, that's what I've been reading about for about the last year, and I've actually been trying to dig up everything about randomness possible. So let me boil this down. There's a point of view aspect to randomness. So I could have a lump of uranium in the back room and a Geiger counter and little clicks out here occurring on a speaker. And everybody would be pretty happy that that's random. The number of clicks per time is related to the element that's sitting in there. So if I measure it over a long period of time, I might be able to piece together even what material that was, because that's what uranium does. That's the half-life and the particles popping out like that. Of course, I'd have to know the sample size, but or I could have one of you back there with a little switch going click, 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 click. And for a short sample, I'd have no idea between the two. You could go click, 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 click. Well, that could happen. I mean, that certainly is random. Or I decide to make a rapid sequence of clicks right there. So there is a randomness in that sense. But you can also look at a sample of the gaps between clicks and apply different mathematical tests to it. And humans in particular are bad at making random sequences with our brains. You can, if you get, I've taught statistics and I've had the students, either one student in the class make up a random string of heads and tails, and the other is actually over there working with a quarter and marking it down. You can tell the stuff that the people make is too random. That real randomness is more clumpy than we expect intuitively. So I can get pretty good skill at doing that. But then there's randomness from the quantum realm. Whenever you're measuring some quantum mechanical process, there's randomness in chaotic systems. So you can have 3, 4, 5 gravitational bodies going around each other, and eventually they go into a chaotic mess. But still, when you look at it over a long period of time, you have these strange attractors, and you have patterns that repeat. You have areas that they don't really go, and places that they frequent. And so it's not really random there too. So randomness is difficult to work with. Computers are not random. So if you ask it for a random number, there's a function in there to do that, but it's not really random. It's not good enough for scientific purposes if you're trying to compare randomness to that. So yeah, it's a mess. I don't know if I'm prepared to go much further than that, but a lot of processes are random based on your point of view and the sample size. So yeah. Anybody else have any random thoughts? Sorry, that was a real question. All right. So that might be a good talk to do sometime. If I can make that exciting enough, maybe I'll do a randomness talk.
Thermal noise is a good example.
Thermal noise, yeah. Yep, absolutely. But still, get enough of source material and you'll get a nice spectra out of it. You get a nice bell-shaped curve or something, Wien's law or something, yeah. But, so on big samples, it's obviously not random. The same thing, if you have just a few gas molecules in a box, you don't know what their velocity is or what their position is necessarily. You get a whole bunch and you can just put PV equals nRT, and a large sample and the randomness goes away. The entire sample becomes very predictable. So, all right, so quantum mechanics, fantastically successful theory. We've got a nice table of all the particles, leptons and quarks, and like that. So I think I want to keep on that one idea. We've already talked about black holes. This is taken from the Theories of Everything talk, which is trying to spin the audience up to speed on black holes. Everybody here for the black hole talk portion we did earlier? Anybody miss that? You were not? Okay. So let's do a recap just so you are on top of the topic here. So a black hole is where you have so much material compressed into a certain area of space that in the simplest definition, the speed of light at some surface around it meets the speed of light. So, the escape velocity meets the speed of light. So a particle here can't get away, just looking at the very simple mechanics of what's going on in here. So everything inside here is beyond the event horizon. It's beyond the point where you can see the events occurring inside. The information won't get out. Now we'll get to Hawking radiation and what it might mean, but there's randomness involved there too. But just in the simplest case, that's what's going on. What we do know is that space and time are being warped. So as you get closer and closer, time itself and space are changing roles, rotating one into the other. So your future right now, standing on Earth, is forward in time. I'm not moving anyplace. The Earth is turning and we're going around the sun and the sun's moving through the galaxy. But from this point of view, staying in this classroom, the only motion I have is forward in time. As you fall into a black hole, your future becomes down. Your future becomes this point, and beyond the event horizon, that's your only future, is spatially down. You can move forward and back in time just by going side to side, but it doesn't do you any good. You're not able to get away and tell anybody about it. So,
If that's true, how do you know what you just said is true?
general relativity equations. Yeah, there's something called a.
Must be true.
Yeah, well, as far as we know, yeah, it works. In fact, we've got a project right now, the Black Hole Event Horizon Telescope. I think that's pretty much its name. I'm kind of butchering it, I think, but they're combining data from telescopes across the face of the Earth to look at our central black hole and the black hole of M80,
M82 or
MA1, MA7, one of those, to try to actually image the space right around the black hole. They haven't released the image yet, but the early data says they've kind of leaked out that general relativity is still working right down in close. So pretty cool. So what we have is space and time curving. So space is arcing down to singularity at its center. Now, as we see when we get into loop quantum gravity, either later today or next week, next month, loop quantum gravity is a different approach to solving this unification between general relativity and quantum mechanics that doesn't allow an actual point singularity. It says there's a maximum density that you can pack the elements that create space together. But right now, just looking at this equations of general relativity, there's a singularity, which means you have infinite density and you have zero space, which once you divide by zero, things get nasty. So we don't like to divide by zero. In physics, it usually means the theory it's got something wrong with it if you start getting singularities out of it. So we know there's a need to understand the physics in this extreme environment, and that's what quantum gravity will hopefully do. When you force marriage between quantum mechanics and general relativity mathematically, when you get down to about the smallest scales you can get, the Planck scale, you get singularities and ridiculous results. They've visualized this is from Brian Greene's book, as a sort of a foamy, turbulent, discontinuous space-time mess. And here, if I want to draw a nice straight line of a function of some process going on, not a problem. I'm going to try to draw a line through here. Well, that's like Brandon's bedroom after he's been playing in there for a few minutes. So you can't walk through there, you can't do physics through there either. And I'm talking about his bedroom. So it's super string theory is trying to do is fix these two. It's what physicists call an elegant mathematical approach to marrying these two together. So again, we've got these four forces, we've got three families and four particles each that we need to explain somehow. And then we have gravity right in here too. When they play with this, starting with like a diamond, going down to a carbon, meshed together, going down inside a single atom, you've got the protons, neutrons in the center, electrons around the outside edge, that when you go down into the fundamental particles, say in the electron is a fundamental particle, as far as we know, it's indivisible. The proton is divisible into quarks held together by gluons, but each of those quarks are fundamental, and when you look inside them, way down at the Planck scale, it's 10 to the minus 35 meters in size or so, you have strings. Strings with a little size, and their vibration, this is just putting the whole theory out in one quick thumbnail here, their vibration determines the physical properties we see up on the quantum mechanical level. So how they interact electromagnetically, how they interact in the strong nuclear force, weak or gravitational force comes from their vibration. So going back to dark matter is something that has a mass to it. It imparts curvature of space-time the same as matter does. It causes gravitational lensing to occur, even though the light goes right through it. It gets bent by space-time with dark matter in it, but the dark matter doesn't absorb the light. Yes? Oh, wow. Nice one. So what dark matter would have would be a vibrational existence that doesn't include the electromagnetic interaction. The way they've approached it is it has gravity and it has a weak and strong nuclear forces in it. That's just a guess. And it would be its own antiparticle. So if two dark matter particles come together, they release, they destroy each other, and they release a little gamma ray radiation. And we're looking for that signal in space. We're looking for a background glow of a certain frequency of gamma ray radiation that would betray dark matter getting together. I don't think we've seen any definitive signal like that, though. They're trying. But the electron would have a different game to play with these than the gluon and the photon and the quark and like that. So you're playing with what features these have to create these particles, all based on what the strings are doing down below. But there's no room in just four-dimensional space-time for the mathematics. To get solutions out of this merger, you need to hop up to, say, 10 dimensions. So you have 3 of space, 1 of time, and 6 curled up space dimensions that give these strings another direction to do their vibrating, to have the features that they do, to include gravity. And there's if you want, you got Brian Greene's The Elegant Universe and I think Fabric of Space-Time is a 2-part book and Nova series that really goes into this in detail. But the mathematics that gives a lead to how these things could vibrate in other directions are Calabi-Yau shapes. And what these are very mathematically complex, higher dimensional Mobius strips. This comes from the question of, all right, you get a strip of paper, you got a 2-dimensional object, and if you give it one twist and bring it around and tape it together, now you have an interesting feature. You have a 3-dimensional object made up of a 2-dimensional surface that only has one side. So you're playing with this dimensionality by giving it that twist. So if you start drawing a pencil mark around the paper, you go around, and you're right back to where you started on the same side of the paper. That's the neat thing of a Mobius strip. And if you cut one in half, you still have a Mobius strip and fun stuff like that. Well, the question they asked, just mathematically, was, can you take a 3-dimensional object and give it a twist and curve it in 4-dimensional space and reconnect it to have a 4-dimensional object that's made of a 3-dimensional surface that only has 2 dimensions on its surface. So you're just upping the numbers. Or can you go 5, 4, 3? Can you take a 4-dimensional space, curve it in the 5th dimension, and get a 3-dimensional surface all the way around? And so they played with that mathematics, and that mathematics seems to be useful in giving these little strings their needed room to vibrate in those curled up dimensions. So I don't know if it's a 10-dimensional, 11-dimensional space curved in of a 10-dimensional surface with a 9th-dimensional thing. I don't know, but
I think we have Brian Green's video here.
okay.
So maybe
One of these times.
we can play it. It's about an hour.
Yeah, that'd be great.
Yeah.
Yeah, the first one definitely. Yeah. So, anybody seen Brian Green's Elegant Universe? That would probably be very useful. Yeah.
But maybe next month.
Next month we can do that. Bring popcorn. So, do you have a microwave in here?
We can bring them.
All right. So what you get when you switch to strings are these nice little closed loops. And instead of two particles meeting in a singular point and having their interaction, I think the battery is dying on this, you have these gentle mergers of strings coming out. So again, if you can get rid of sharp things, people don't get hurt. So pretty quickly, we had about 5 flavors of string theory emerge from different research groups and mathematicians and physicists, and people began to despair. Like, what are you going to do with this? And along came, his last name was Whitten, right? I can't remember his first name. It just left my brain. Stephen Whitten? Oh, no. But maybe I have his name here. Nope. It'll come to me. He proposed that if you just add one more dimension, taking everything up to 11, then these different string theories actually all mathematically become the same. So it's very much like the blind people around an elephant. Everybody was feeling a different part of the elephant, thinking I had a snake or a tree trunk or a brush or whatever. And actually, you just had an elephant. So he coined the term M theory. He's kind of cagey as to where he got the letter M. In Brian Green's video, it's the W for Whitten upside down to make an M. Whatever. And the mathematics, though, is so intense that some speculate it'll be decades or centuries before we can find our universe. There are so many Calabre-Yar shapes that are valid mathematically but don't create our universe, that there's just trillions and trillions and trillions and billions and trillions of possible solutions to this. So right now, unless someone has a fantastic insight to jump over large chunks of these and be able to throw away classes of these solutions, it's a trudging through the forest and macheting your way through the underbrush to try to find our universe, which is not very satisfying. That doesn't make people very happy, and many point to this entire approach as not really being science. That, yeah, you've got an elegant mathematical approach to explaining how these two areas of physics may work together, but there's, at this point, no way to test any of these. If they mathematically work, yay, but we can't probe down at the scale of the string, 10 to the minus 35 meters. What the analogy they use is an oak tree on Earth compared to the diameter of the universe is the same scale ratio of a string to us in the laboratory. So, you know, it's way beyond what our current physics can do. I think even to make progress towards it, you'd have to have a particle accelerator around the circumference of our galaxy, taking particles all the way around and smashing them together, accelerating them the whole way. That's a serious engineering task. So, others have proposed using the universe itself, looking at cosmic rays emitted from violent astronomical events like supernova far across the universe and trying to discern the nature of space-time from effects left on the particle as it traveled. But it's right now more elegance than it is hardcore physics. There is another side of this string approach. Some have taken the strings, saying, well, it could have strings left over from the Big Bang itself, cosmic strings that got stretched out so that they span across the universe. And I think if anybody saw, was it Star Trek Generations, the movie, you had the ribbon called the Nexus that Kirk and Picard were doing stuff in, and like that. I think they kind of twisted this idea to make a nice sci-fi element there. But if those did exist, if there were some gigantic stretched out strings out there, they would have a lot of gravitational tug associated with them. So we might see them through gravitational lensing. I've not heard of any observation that suggests that they're there. Gravitational lensing, again, is because space-time is curved. When light, trying to go on a nice straight path, encounters a gravitational well around a star or a large galaxy or the dark matter bubble around a galaxy, you get the much more distant galaxies warped into these arcs. So these are all galaxies being randomly warped by space-time, which is really cool because in just the right situations, these big bubbles of warped space can act like a second telescope. And you can get the light of a much more distant galaxy magnified, though distorted, and sent to our telescope. So we've had some real records set in observing actual galaxies made by combining, I think, like Hubble and like that with gravitational lensing. I think one of the earliest normal stars, individual stars, has been identified this way as well. So,
John, how
yes.
do you know that the light that you are seeing is being lensed and is not at the distance of, would it be from the distortion or?
You could see it's redshift still. So the expansion of the universe between here and there would be very different for these lensed objects than the one in the foreground. Yeah.
And in addition to it being distorted because
Mm-hmm.
of the optical
Yep.
characteristics.
You got it. So you get, sometimes you can get a real object in behind, straight behind the object, and you'll get a double image on either side like that. So you can get, Einstein predicted you might get a cross like this or a ring if you have just the right alignment of objects. And once telescopes got good enough, we found those out there, which is really cool. And I've seen this kind of pop up briefly in the literature now and then, that if that's one object and that's one object, the photon coming from the original stars have to choose a direction to go around this foreground galaxy before getting all the way to us. What you have is a cosmic double slit experiment. And they've said if you make an observation of this, then you're actually causing the wave function to collapse way back here across the universe and decide which way to go or not. So some have proposed using lensing or the light of quasars on opposite sides of the sky to help actually introduce better randomness into quantum mechanical computing systems. So that just blows my mind. I'm sorry. There's people who obviously paid for understanding this stuff better than I. So. Now, this is what I was talking about with black holes earlier, that we can look at, by simplifying the dimensions, knock it down so our little human brains can take it. If you turn three-dimensional space into a nice flat plane that goes right through now, I don't know why this is 2001, you guys are not in 2001. This is obviously an older textbook. But here's now, then the future is up and the past is back. the speed of light, if you turn on your flashlight here, would leave you at this, out into the future, would get away only this far at the speed of light. The speed of light is constant. If someone had flashed a flashlight back here in the past, and you looked today, make that 2019, then you would see that flash just reach you along that diagonal line in space-time. So we have this past cone of everything that you could have done below the speed of light, because you can't go faster than the speed of light. So every place that you could have ever visited and traveled, every place you can get information from, events you can see in a telescope, all are in this cone behind you, and all that you can ever do in the future, because you can't go faster than the speed of light, is in the cone ahead of you. So over in these sides is an elsewhere space-time that is inaccessible. Now the events that occur there might eventually enter the future light cone. So like right now, I don't know what's happening to a certain rock on Mars. I also can't get to Mars right now and brush my teeth. So those things are elsewhere possibilities. I can imagine them, but I can't do them. So this is a Minkowski diagram, and it's a nice way to envision some of the limitations of space and time that light brings about. If you have a cosmic string, or you could play around with the singularity in a black hole, you would widen this cone here, so as you travel up, you could actually go around and then continue. So at this point, you could meet yourself by basically traveling back in time. So you get to goof around with your world line if you have extreme physics allowed. Again, cosmic strings, not observed, it's just a mathematical possibility. After 2003, introduced to this whole string theory idea, were the idea that, well, not only can strings be strings, you could also play with membranes to one dimension higher. So you have a now flat plane. And so it's called, shortened to branes, B-R-A-N-E-S. And so you can have branes of any number of dimensions, and so they call those p-branes. You put in the number of dimensions in for p. I know, physicists, they stay up way too late at night. So we might be in a four-dimensional universe, 3 dimensions of space, 1 dimension of time, and we could be separated from another four-dimensional universe by a 5th dimensional gap. And some have proposed that gap and that other four-dimensional universe could act like a shadow universe. And this could be where gravity goes to vacation, basically. And that could help things out. So do I have a picture of that? I don't have that. Oh, I guess I got that elsewhere. So basically gravitons are not held to our brain, our membrane, but can spend some time off in the other membrane. And that helps account for the fantastic weakness of gravity compared to all the other forces. All right, so these other dimensions allow the parallel universe model to come in. Again, there's no evidence that we have parallel universes out there, but some of these are the consequences of the mathematics that you play with. Are the mathematics complete? Is our physical understanding complete? No, we're at the very ragged edge here of physical understanding. But if the universe is flat, as we've talked about last year, and I kind of recapped a moment ago, that our best observations of supernova and the leftover glow of the Big Bang show that we're not so curved that we're going to collapse in the future. We're not so negatively curved that without dark energy we would never collapse. Dark energy is a different game. But we are so close to flat that the universe acts as if it is infinite in size. They're very, very close. And if you just do the math, looking at our bubble of space-time, of what we can see out to the limit of observability, all the stuff that is in our past light cone, which is bigger than the cosmic microwave background radiation glow. It's actually, I think I get this right, we see 13.7 billion light years back to the Big Bang by age, but the actual bubble, the Hubble bubble, I think is 40 billion? I think it's 40 billion. So that's the limit. Beyond that, everything else happening in this big happy universe is outside of our light cone. We never get information from those parts of the universe into our past and see it with a telescope. And then dark energy complicates this further because it's shrinking that bubble as time goes on. But if this is our observable universe, say out to 40 billion light years, with a very, 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 very large or infinite universe in reality, there's a point where you run out of configurations of particles, energy, and space inside. I mean, just so many combinations you can do. And eventually, there's a bubble out here someplace that it repeats. It's just got to. I mean, if you have enough room and you're drawing all these bubbles of random volumes out at 10 to the 10 to the 122 meters away from us, we're doing this exact same thing right now. And not just in that direction, but that direction, that direction, that direction, that direction. There's a lot of yous and I's all sitting in this classroom. Because you just run out of possibilities. It's just pure combinations. There's other theorized multiverses, or those would be ones in which we have a very huge bubble in which eventually we can repeat or not. But there's others where physics run differently. You have different bubbles out there of that. That has less evidence than the other ones we play with, so I'll just move on. Going to another way to solve problems in quantum mechanics, we have the Everett's parallel or multiverse model, where we have parallel universes where every decision quantum mechanically spawns another universe. And it actually helps with the mathematics. The big headache that even books like this are fighting with is what's called the Copenhagen interpretation of quantum mechanics, that when you have an electron or a photon or an atom, it's really a probability wave. There's something called Schrodinger's equation that explains how this wave works. The mathematics is fantastically accurate. You've got this probability based on the square of the amplitude, is that right? I just heard that click and my sound went off, didn't it? No? Okay. Sound just changed though, didn't it? It's not as loud.
Could be.
Someone want to go back and make sure that the little thing is bouncing on the screen for me? Yeah, I just heard a click. That's strange. And so the Copenhagen interpretation of what happens when you observe an electron or a photon or an atom is that this ghostly, is it good? Okay. Ghostly wave function, this probability of where the electron is, collapses down to be at a certain spot. It just happens like that. There's no mathematics that describes this collapse. It's just kind of hand-waved in. But it seems to work. And we've built, again, the whole technological world around us on these equations just fine. So it's almost like that little collapse idea is a convenience for our comfort that something is happening that we can talk about. What Everett did is went a different way. He said, no, there's no collapse. What happens when you observe something that's in this fuzzy probabilistic area is that decision occurred, and now you know where the particle is, but all the other possibilities spawned parallel universes. Okay, but the math works really well, and it is still holding to today as a viable alternative interpretation to what's happening in the weird world of quantum mechanics when an observation is made. Now, a lot of observations are being made all over this big, huge universe to create reality itself. Particles interacting, stars are shining, galaxies exist with gravity pulling and tugging on each other in their own parts, and all this is going on. But according to this interpretation, every roll of the dice, quantum mechanically, creates more universes. So every possible thing that you've ever could have done exists out there in a parallel universe. We played with this in the section 3 part of this lecture, so you could go back and get an expansion on this idea by looking at the earlier class videos. But one of the observations this helps with is, again, the double slit experiment. You've got one slit, you put light through it, you get a spot on the wall. What everybody would expect. Photons are acting like photons. Put 2 slits in there, send light towards it, and you get an interference pattern on the screen with the dark spot, light spot behind the dark wall, and then dimmer bands of light going off in both directions. And that's because then, since you are observing with 2 slits, light acts like a wave, and the waves interfere, and the high points add to the high points, get you the bright spot, the low points add to the low points, give you the dark spots. The weirdness is you can shoot 1 photon an hour at this experiment, and it'll go through and make a dot on the wall, and it just keeps changing, doesn't it? But be it electrons or photons, you keep shooting one at a time, let weeks and months go by, and the interference pattern still occurs. What's it interfering with? You're only sending 1 photon through at a time. There's no photons to interfere with other photons, and photons can't be divided. Electrons can't be divided in half to go through both slits, but they act like they are. That's the wave particle weirdness that we see down at the quantum level. Well, whatever it says is, as they part ways, as the new universe is split off with each decision, they're interfering with each other in that parting of the ways. And so all the possible paths that the photons could take occur, interfere, and then they're inaccessible to each other except the one that happened in the universe path that we're taking. So it explains the mathematics well. It's very nice mathematically. So, I think I just did my follow-up slides. So that's wave-particle duality is what we're dealing with. And particles and waves are just different entities. As they say in Brian Greene's book, water is either a drop or it's a big wave. But thinking of water as particles and waves at the same time just is counterintuitive. I mean, they operate differently, but they don't. So as you send an electron into an electric field, it acts like a wall, and you would expect it to bounce off because it's a particle. But since it acts like a wave, part of its little tail goes through, and that is the % chance that it goes through a solid wall. That's what quantum mechanics allows. This is where we get semiconductors. This is the basis of transistors and everything that we've built digitally. And so, see, I didn't have to do all that with my hands. There's the light bulb making one spot. Here's what's really going on with one bright spot and waves. You throw a pebble in, you get the waves out like that. So the 2 slits give you that interference pattern. Put the 2 slits, you've got the waves coming out, adding and subtracting from each other, giving you that interference pattern. So, and this is over weeks of time, doing one at a time. You can see they add up. I knew that was here, I just wasn't seeing the slides come up. So, who needs slides? So that is bizarre behavior, one at a time, making the pattern as if you're putting a whole beam through at the same time. Now, if you make an observation, if you take a look and to measure which slit a photon or an electron went through, the interference pattern vanishes. It says, uh-oh, you're looking at me, I'm going to make a decision earlier. And so that observation ruins the interference pattern. And you get one mess on the other side like that. So that is going back to the light picking the path around the galaxy. The physics is the same. Once you observe it, you've forced it to make the decision by looking at it. So if you add up all the possible paths that light can take from one to the other, you get the same pattern. This is a contribution by Feynman. I think, is that what he got the Nobel Prize for? I'm not sure. I know he did for explaining some of the mathematics behind antimatter, but all these paths together add up, which gives support to Everett's picture of all the paths still existing, at least for a moment, and interfering with each other in some way. Now, to do the math to explain all the possible patterns, including the photon coming back around here and going there and going here and being absorbed and re-emitted and coming back over here, I mean, all the things that could possibly happen is prohibitively ridiculous. But if you nail it down to the most likely ones, that explains the bulk of the reaction that comes out the other side, and that's what physicists do. So this is the membrane picture, that it's possible that gravitons hop out for a while and spend some of their energy in another parallel universe before coming back in. All right, so other versions of multiverses include multiple ways physics work or space-time naturally curves, but I think that's more speculative than anything else, and we don't need it. If you don't need it, why bring it into physics? But someone did and made that pretty picture. And it's called a level 4 multiverse, and I'm sure there are physicists and mathematicians working on the mathematics behind this, but we'll move on. So this membrane approach is another way to explain the Big Bang without a singularity. Again, we really don't want singularities. Dividing by 0 is pretty bad in most cases. And so as the universe expands and expands and expands, it's theorized, the repulsion between this other four-dimensional universe separated from us by a gap in fifth-dimensional space may start to close. The two universes start to attract and touch, and when they touch, you get our universe filled with high energy, extremely dense material that then immediately starts to expand away in every direction. And so in they come, touch, and this way the Big Bang happens universe-wide, all at the same time, and you have a very flat universe before, and you have a very flat universe afterwards. So this gets rid of a singularity, and it gives us the same present-day look of a universe cooling and expanding, creating galaxies and material until it becomes empty enough for them to drift towards each other and do it again and again and again. So you have a cyclical Big Bang in this way that takes away one singularity problem. But again, experiments are what we need, and we don't have a way to do this. We're talking about things 10 to the minus 35 meters. The time it takes light to go across a little space, 10 to the minus 35 meters in size, is 10 to the minus 44 seconds. And those are just ridiculously beyond physics for the foreseeable future. Again, this 10 to the minus 35 is the smallest theorized size you can get in space. The reason being that as you probe to smaller and smaller scales, you have to use more and more energy to do it. So if you're going to probe inside of a proton, you got to smash things together with more energy. If you want to go even further down into what quarks are doing, you've got to use even more energy. That's why we tried to get higher and higher energy colliders. Yes?
What's the highest or shortest wavelength photon we've ever observed, either from the universe or created here?
I think the highest is going to be, it's going to be a cosmic ray, or something coming from the universe.
Well, that's
Right. And I think, gosh, this is dragging up a random trivia bit, but I think there was a cosmic ray shower of particles observed. So it's the byproducts of everything showering out of this cosmic ray hitting some atom up high up in our atmosphere, and it just cascaded down, got picked up by things. It was the energy of like a grapefruit traveling at 25 miles an hour. It was something like that. So that would be the shortest wavelength, highest energy one. You'd have to do the calculation of what something like a pound in mass or a few pounds in mass going 25 miles an hour. It's very big for a single subatomic particle, or a photon. Yeah, so the natural processes have gone far beyond what we've done. And that's what gave the physicists confidence that when they turned on the Large Hadron Collider, that we weren't going to get black holes that were going to swallow up the Earth. That natural processes would have already been raining micro black holes on us since the Earth formed, and we would be gone. Same thing with neutron stars. They're even more on the balance. So if one of those got hit with too many of these, it would black holatize very quickly. You wouldn't have neutron stars in space. So we were confident that we would not be destroying the Earth by turning that on. So yeah, to measure down to the Planck scale, the photon would have to have the energy high enough to briefly turn into a black hole. It would evaporate immediately, but we're not going to get information out of that scale. All right, so the problems that I've kind of touched on here is that we really can't measure things at the string and Planck scale. String theory doesn't create its own space. It assumes this background space, sort of a stage that the physics is occurring on. It assumes that space is smooth and continuous. In fact, we wanted to get rid of that foamy weirdness in space. It assumes, most versions, that time is continuous, that its reactions are occurring, and that you don't have odd things popping forward and backward in time. And space-time may come in tiny chunks, and we have observations being made of cosmic rays, where we're trying to figure out whether that's the case, whether these Planck units are actually, the tiniest bits are actually a physical limitation in the universe. Maybe the universe is granular rather than a continuous nothingness in the background. And there's just stuff we don't understand yet, like dark matter and dark energy. What about new particles and new forces? We've touched on already that we have dark energy and dark matter that we don't have an explanation for yet. Dark matter is this gravitational containing something that warps space and time, but light goes right through. Dark energy making up an even greater fraction of the energy budget of the universe is accelerating the expansion of empty space, but we don't know what it is either. Is it something built into space-time itself? Is it an additional anti-gravity-like force? Is it related to gravity some way? We'll get to that after a break. Let's take a 10-minute break and refresh your brains. I know, we're at the jagged edge of physics and trying to figure out what it all means.
dark matter really isn't just non-incandescent matter?
It doesn't convince everybody. The question was, what convinces the dark matter exists? It doesn't convince everyone, but the fact that we see gravitational lensing occurring around clusters of galaxies, around large galaxies, we know that something is warping space-time more than all the observable stars and dust that are there.
So that doesn't cancel out the possibility of a black hole?
It would, because we would see its effects as a central, from a central location. So you'd have velocities in the middle of the galaxy much higher. The amount of dark matter around the typical galaxy it's roughly a 10-to-1 ratio. So 10 times more dark matter than there is galaxy. So it's like our galaxy, it's much beyond. So what the effect is that the outer part of the galaxy is moving faster than it should, just looking at gravity. Right. So that implies a halo source rather than a point source in the middle, because otherwise it'd be much slower out and much faster in the middle. So yeah, it's the best model for most, but again, some are trying to modify Newtonian dynamics to explain it. Just saying, at a certain scale, the R squared in the bottom needs to be modified in some way that accounts for a faster velocity and more warping of space-time than gravity would be expected to do, given that amount of mass. But I don't think anybody's been successful in explaining all the phenomena that we see with any formulation of Newtonian dynamics with a bunch of extra terms or modifiers. You know. Not that there isn't that out there, but no one's been successful yet. Yeah. So we have, I mean, this is a real serious problem. We've got two big branches of physics now working together. We have most of the energy balance of the universe unexplained. There's a lot of unknown here. And we have one of the leading candidates, string theory, is not really provable by observation. It's a headache. It is. If you're frustrated, welcome to physics. So it has mass and gravity. It doesn't block or reflect light. It doesn't interact with electromagnetism. It does the gravitational lensing. There's the typical galaxy. There's the halo that would account for the actual gravitational mass of the galaxy, looking at how it rotates and how it bends starlight coming through this part of space. What's dark energy? It's a repulsive force that seems to be pushing galaxy clusters apart faster and faster. Is it a new force? Is it a field that fills all of space? Is it built into space itself? We just don't know. Do we need to correct the equations of general relativity, a modified general relativity theory that says where you have huge amounts of empty space, you have a negation of gravity for some reason. It's not a clean, nice solution either. It's embarrassing. So, and in the end, dark energy is expanding the universe in an accelerating fashion. It's eventually going to dominate the universe. This percentage back here is going to continue to grow. It's grown greatly since in fact, it's almost negligible in the early universe. Now it's almost 70%, eventually be 99.99999, etc. And so the pulling apart of empty space, or what counts as empty space that's being pulled apart or accelerated apart, is going to drop until galaxies are being pulled apart. Eventually the Hubble bubble will only be right outside the confines of our galaxy. We won't see any evidence of the Big Bang. Future astronomers won't even see other galaxies. And then eventually dark energy could pull the galaxy apart, stars apart, molecules apart, and that's called the Big Rip. So here we are 22 billion years before this possible Big Rip. 60 million years before the Big Rip, the dark energy pulls the Milky Way apart. 3 months before the Big Rip, the solar system breaks apart. The space expanding between us and the sun becomes so rapid that goodbye gravity, goodbye sun, away we go. 30 minutes before the Big Rip, the Earth explodes, and 10 to the negative 19 seconds before the Big Rip, atoms themselves are ripped apart. The empty space between electron and proton is too much, and then downward it would go. So the universe would be totally destroyed by this. Possible? We don't know. That's way beyond. We're not even sure this is true. And we see evidence that time doesn't actually figure into physics. I mean, quantum mechanics and general relativity can easily be derived to be timeless. The equations work forward and back without time. So time could be an illusion where all of the future and past are like looking at a reel of film or a DVD of a movie. It's all right in front of you. If you want to understand it, you have to go through it sequentially, but we're going to play with that in the information part next. So, I think we're going to do...
Two DVDs, I'm sure it's more than an hour. It doesn't say on the box how long the playtime is, so I need to load one and see.
Okay. You guys want to switch over to Brian Greene's DVD? We can do string theory from his entertaining point of view the rest of this time and next. And then we'll pick up with this other version of reality after string theory gets a good illustration. Does that sound good? Because most of the energy and most of the money trying to link and answer all these problems in physics has gone to string theory. It's got its strong detractors, and we'll talk about that in the next section. But, and that'll also give me a chance to pull these books in. I might be able to give you some hot takes on reality and quantum mechanics. Let's see, when was this book published? Yeah, because we'll have to just supply a link to it because we can't put copyrighted material. Yeah. So switch over. I think if you go to pbs.org, you can see both of Brian Greene's shows on Nova streamed. I think they have it as a free streaming service, but we're not going to play with copyrights. So any questions as he plays with the equations? So this is a 2012 approach to solving this, and so in next month I should have that all in my head.